No, I didn't. But you have the problems. I stick pretty close to the review, so if you go through the review problems and know how to do everything, you should be fine.
Okay.
So,
And the exam is the whole period, right?
the first 2 exams, I think, is the whole period. The last 2 won't be. The last 2 are a lot shorter. So the first 2 exams, the whole period. The last 2, I think it's 45 minutes each.
So a whole period is like 10 questions?
No, it's less. It's like 5 or
Okay.
6. With a bonus, yeah. So you're going to have to show all your work. They're not going to be like quizzes where it's just you give me the answer. You're going to have to write stuff out, and you'll get partial credit and stuff. Yes? 10.7 to 13.3. It's in the syllabus. I tell you what topics each exam covers.
That's science squared too. Otherwise,
Yeah, so for quiz 2, just a few comments. Well, a lot of people messed up on the definitions, especially a lot of people. And I actually mentioned that you should actually write, if this shows up in your formula, you should actually write out what it means. Right? I expected you to put the radical of blah, blah, blah. So a lot of people missed that. This actually happened quite often. A lot of people said this. Is this true? No. The integral of 1 over y is ln y, not the derivative, right? This is y to the minus 1.
Yeah.
The derivative is minus y to the minus 2.
Exactly.
A lot of people, I saw ln y's all over the place. What else was there? Right, so I guess a lot of people got mixed up because I mentioned before that R was x of t, y of t, z of t, or something like that. But then later on, I asked you to write out the formula for this, and some people got it almost right. They said something like ABC, x of t, y of t, times the radical of, they said x prime. And then they put in a z prime square.
Z?
Right? Yeah, that's, you're not supposed to put that in, right? You only care about the guys that show up here. If a z was here, then you need that. If it's just x and y, you don't put that part in. Right? You follow what variables you're given. Yeah, that was basically it. Yes. Suppose we can move on. So we're going to continue with 13.3. Recall the last few things that we spoke about. We spoke about the fundamental theorem for line integrals, right? And that basically said that the integral along C of a gradient function, dr, is equal to the original function evaluated at the first endpoint, the last endpoint, minus the function evaluated at the first endpoint, right? Here, this is if this guy is continuous, right? Then this thing applies, and here your C is parameterized by R of t for t goes from
For our purposes, the gradient will always be continuous?
Come again?
For our purposes, the gradient will always be continuous?
Yeah, pretty much always going to give you something that's continuous.
Okay.
But we know that, we learned that the fundamental theorem line integral says that if you're doing the line integral over a gradient field, it's actually what we call independent of the path. So we also learned that. So it doesn't matter what the curve R is, it only matters what the endpoints are, and you can figure out the integral, right? Right, so we also learned
And
that.
conservative.
And, come again?
Conservative. If it's independent of that, it's conservative.
Right, because we know that the gradient of f, if f equals a gradient of some function, then we say f is conservative, and that terminology really comes from the work interpretation, right? If you actually do work around a closed path, you get 0. You actually conserve work for conservative vector fields. We say f is conservative, and the scalar function from which we take the gradient to get f is called the potential function of f. So we covered that. Right, so these are just a few facts that we're picking up now with.
Why is it called potential?
Come again?
Why is it potential?
It's that terminology probably comes from physics interpretation, but that's just yeah, you like voltage. Yeah. So, but these are just names. It's just if you see this, you should know that that's what they're talking about, and if you see this, you should know that that's what they're talking about, basically. Right. So these are just proper names for some of the things we've described so far. Right. So that's where we left off, and I believe we spoke about independent of path if it's the integral is 0 for every closed curve. So now we're going to move on because we're going to state some other theorems and we're going to need to know some more terminology. So we're going to continue with a definition of what it means for a set to be open. We're using a very watered down definition here. It does not contain its boundaries. Right? So, for example, x squared plus y squared less than 4. This defines an open set. Right, in R2. Right? This is just the open circle of radius 2, right? It doesn't contain its boundary.
So it's like an open disk, basically.
An open disk, right. So any set that doesn't contain its boundary, you call it open. Right? And a lot of our theorems will only work for open sets, so that's basically what it means. Right? Come again?
Why?
It has to do with the definition of derivatives and stuff like that, because you have to be able to zoom into, it's a local property, you have to be able to zoom in and you have to always have this little segue to make sure a derivative works, basically. Because derivative at a point, it's defined in terms of limits, which means you need some leeway between the point, right? You need some space to the right and left of the point for the limit to exist. And so, for derivatives to work, we need open sets. So, we're going to do that. And we're also going to mention what it means to be what we call connected. Right? So when we mention connected here, we're talking about path connected. I'm going to define that. There are different types of connectedness, but when we say connected in this class, we mean path connected. If any 2 points connected by a curve entirely. Right, so example. You have a set looks like that in R2 that's connected, right? Because any 2 points you pick, I'd be able to draw a curve in there and connect them, right? If I have a set in R2, it has a hole in it. Doesn't matter, right? Because any 2 points over here, I can connect it with a curve that's still in the set, right? Not connected means if my set is defined by 2 open sets that don't touch each other, then if I pick a point here and I pick a point there, I cannot connect them with a curve that stays in the set, right? So any curve that I do here would have to exit the set to actually connect to the other one, right? So a lot of things that we're going to do deal with open and connected sets. Because of course we're doing line integrals, we have to stay on a curve that's going through our set. So we're not going to want anything that's disconnected. Here's the thing. Suppose a vector field F is continuous on an open, connected if F dot dr is So this is a theorem that says if we know our integral is independent of path, it automatically means it's conservative, right? And conservative means you will be able to find a function such that you can take its gradient and get that vector field, right? Which, by the way, is not a trivial fact. Not all vector fields are gradient fields. So, in other words, the fundamental theorem of line integrals does not apply to everything. That's basically what I'm saying. Which is a very important fact because I've actually had some questions via email where students were sort of confused about this, where they said, you know, they asked me if the line integral of a vector field around a closed curve, it is always 0. The answer is no. It's only 0. You know definitely that it's always 0 if your vector field is conservative. Otherwise, if it's not conservative, the line integral could be anything. Right? So make sure that you know it only works for this kind of vector field. Right? So now, of course, the question is, that should be the obvious question, right? So if you know something is independent of path, the questions would be, well, I know that this function exists, but how do I find it, right? And moreover, how do we know it's conservative in the first place? So those are the two questions that the rest of 13.3 is going to answer, right? So we know that the fundamental theorem of line integrals says if we have a conservative vector field, a gradient field, and then it's independent of path, which means we'd be able to find a scalar function f that if we take the gradient, we get this guy. So the question is, how do you know in the beginning that you have a conservative vector field? And once you've determined that, how do you find the f that gives you that vector field? Right? Because the definitions that we have so far says, you know, it's conservative if the line integral around a closed path is 0 for every closed curve. But there are an infinite amount of closed curves. You can't check that, right? So we're going to discover how we can actually check that it's conservative, a really neat way to check. And then once we know how to check, we're going to say, how can we actually find that function? Right? Which leads us to more definitions. Talk about simple curves. Simple curve is just a curve that doesn't intersect itself, right? So that's a simple curve. That's a simple curve. It's not a simple curve. This is not a simple curve, right? That's what simple
3D.
is. Huh?
Unless it's 3D then.
Come again?
Unless it's 3D then.
Right, I mean RT. Well, it's possible that it's so the problem is here it intersects itself. Once you intersect yourself, you're not simple, right? So that's what a simple curve is. Yeah. This section is a lot of definitions because you're going to be using this vocabulary for the rest of the course. So they're really introducing a lot of new terms here. So we're going to have to, make sure you know all of them. We're also going to have theorems that only work for simply connected regions, and I'm going to define what that means. We call a region simply connected if every simply closed curve only encloses points in the region. This is just a fancy way of saying it doesn't have holes. Every simple closed curve in the region. So, for example, here's something that's simply connected. Just like this set here. Right? Because every closed curve that you can throw inside this guy will only enclose points in that curve. If you have this region, though, and there's a hole in it, right? Then I could create a simple closed curve inside this region, but there will be points on the inside of that curve that are not in the set itself. And so we say that's not simply connected. It has holes in it, right? We don't like the holes. Now, another theorem. It's going to tell us, it's going to start answering this question. Right? Turns out that we can only fully answer this question if we have that condition. We have to be on a simply connected region. Let f be a two-dimensional vector function. So it is a two-dimensional vector function. On and open. Simply connected domain. here's the important part. Partial of p with respect to y is equal to the partial of q with respect to x. Right, so once all these conditions are fulfilled, and you know that these partial derivatives are equal, then f is conservative. That's the conclusion, right? So for two-dimensional vector fields, all you have to do is make sure that these conditions are fulfilled and then do this check. If the partial with respect to y of the first component is equal to the partial with respect to x of the second component, it is conservative. You will be able to find a function f. Yes?
What if we have a closed curve, and although it's in a domain that's not simply connected, the curve goes is in a simply connected area of the non-simply connected curve. I mean, domain. I mean, what in that case?
You'd have to redefine the region.
Oh, I see.
Right, so you have a hole here and you have a simple curve here.
Yeah.
I mean, you could only make fantastical claims like this, like in a region over here.
Okay.
Right, you want to make sure that you don't go over these holes. Because then you'd have things like your derivatives are disappearing, they don't exist over here, you know. At a hole, crazy stuff can happen, you know. So you really want to be safe by making sure you're in this kind of situation. Yeah. So you just call it a different region or something. All right, so I think that's most of the theory. Now we get to do problems. Good. So it's starting to get bored writing down all this stuff. Okay. So now we are going to talk about, first, how to check that something is conservative. We know for a two-dimensional vector field, this is how we do it. For a three-dimensional vector field, it's a different test, right? So this only works for two-dimensional vector fields. You do this test, right? And the test for 3 dimensions we will cover later, but for 2 dimensions, this is it. And we know it's conservative. So here, let's do some examples where we're going to check these vector fields. Determine whether or not until everyone catches up.
Is that true because of the second derivative? Meaning if you do partial derivatives on both sides, the second derivative is actually equal to each other? Like if you
No, it's not the second derivative. Basically, this makes sure that you can find this function. It's one of those conditions, and we'll see it expand more later. But basically, we can say if we're on a region that's open, doesn't contain its boundary, and it's simply connected, means it doesn't have holes. So if you're on an open set with no holes in it, and this is true, then your function is conservative. And now we're going to actually do that test. Right? So A.
Just 2i, 2i.
Right? So let's see. First, note. The components are polynomials. What do we know about polynomials? Right? They exist everywhere. Their partials exist everywhere. Right? So we have the continuity. We have partial derivatives existing, and that's fine. Partials exist and are continuous, etc. Right? So that check works. Right? Now, here we know that P is equal to what? 2x plus y squared. The q is equal to 2xy. Right? So if I take the partial of this with respect to y, remember you think of x as a constant, differentiate this guy, you get 2y. Now we're going to take the partial of this with respect to x, which means that your y is a constant, so you differentiate a function of x, just leaves you with a constant. Right? This means that py equals qx, which coupled with these facts means f is conservative. We will be able to find a function that when we take its gradient, we get exactly that vector field. Right? And that also means that if you take a line integral of this guy, it's independent of path. It also means that if I do a line integral of that guy around a closed curve, the answer is 0. I actually don't have to do it, right? All these facts just fall into place once I know that it's conservative, right? So this guy is conservative. What about B?
No.
The answer is no, because in B, you have P is equal to 3xy plus y squared, and your Q is equal to x squared plus xy. And the partial with respect to y of this would be 3x plus 2y. Partial with respect to x of this would be 2x plus y. Right? That is, py is not equal to qx. That is not conservative. Right? So it means that if I was taking a line integral with this vector field, it's not independent of path. The fundamental theorem for line integrals does not apply, and it's not guaranteed that if I take the integral around a closed path, I get 0. Right? It means there also that there is no scalar function. A function does not exist for which I can take the gradient and get this. Right? I can never find a function that the gradient of it is this guy. Right? So if you think I gave you a vector field and I said, oh, do this line integral on this closed curve, and you want to say, oh, it's just 0, I don't have to do it. You basically have to do this check. If this works out, then you're like, oh, it's just 0. It's a trick question, I don't have to do it. Well, if it's not, then you're like, oh, you have to actually do the whole thing, because then all bets are off.
Does this translate to 3D somehow?
Yeah, there's a different test for 3-dimensional. It's not simple like this. It's going to be a little bit complicated.
So the 3D works in both 2D.
Huh?
So the 3D one will work in 2D, right?
The 3D what?
Will the 3D work in 2D or no?
What do you mean work in 2D?
Use the 3D test for 2D.
No, you just use this test.
Okay.
The 3D test is going to be different. It's not just an equation that you're going to check. It's going to be like this vector function. You use the curl basically in the 3D, which is in 2 sections of it, I think. So don't worry about it for now. For now, we can test 2 dimensions, right? Let's see. Okay. So now that we know this function is conservative, how do we find potential function? Right? That's the question, right? So it's conservative, which means there exists a function somewhere where if I take the gradient of that function, I will get that vector field. The question is, how do I find that function? Because if I want to apply the fundamental theorem for line integrals, I have to know what the function is, right? The right side of the equation says plug into the potential function. Well, I need to find it to be able to plug in, right? So now we're going to discuss how you actually discover a potential function once you do the check and you know one exists.
Professor,
Yes?
if you take the integral of the derivative, you just get the function, right? Plus c? Like,
Yeah.
So Like if that's what essentially we're doing.
It's going to include that, yeah. So you're already on the right track. I was going to discuss that. So let's discuss this, right? So if f exists such that the gradient of f equals f, then what must actually happen? Right? So we remember from our formulas that if f is a function of x and y, we're only in 2 dimensions for the moment, then gradient of f is what? Yeah?
dx and dfdy.
Right, partial with respect to x, partial with respect to y, right? Now if I say that this is actually equal to this vector function f, which I define to be p and q, what does that mean? The p must be equal to that, the q must be equal to that. In other words, it means if I know the p, I can think of that as the partial with respect to x. So if I want to get back to the original function, I just have to integrate with respect to x. The q is the partial with respect to y. If I want to get back the original function, I just have to integrate with respect to y.
And that's why when you do the partial derivative with respect to the other one, they equal each other.
Yeah, that's why they have to equal each other. Because you're you have to make sure that condition works so you know you can go back.
Yeah.
Right? So alright, so now we're going to play the game of back and forth to try to get to these functions. There are 2 methods that we're going to use to do this. There's method 1. Now, in method 1, this is the conventional method. For those of you who actually did 391 differential equations, you've all seen this method before. It's actually the exact method you use when solving exact equations in differential equation. Right? You might have noticed that, because that's exactly what in when you're doing exact equations, that's what you look for, right? If you had something that looks like this, it's not important. If you didn't take differential equation, you don't have to write this down. Don't worry about it. Right? They usually use m and n. Right? Now if you want to solve this guy, remember the check that you did was you differentiated this with respect to y and that with respect to x, and if they were equal you called it an exact differential equation. And what did you have to do to solve this? You had to find a function that when you differentiate with respect to x you got this, and when you differentiate with respect to y you got that, right? Yeah. So that same method that you used to find the function, that's exactly the same method we're going to use to find this. It's sort of long. So after that I'm going to show you another method which is shorter, but you know it has a catch to it that you have to look out for. Right? So I'm going to go through the method first.
This one doesn't have a catch and it works.
No, this one won't have a catch, right? And the nice thing about this method is if the function is actually not conservative, then when you're going through the method, it won't work. Something would break apart, right? In the second method I'm going to show you, it's going to give you an answer all the time. So if you did your check wrong in the first place, then you'll never know, right? You have to like double check at the end, right? But this one, it's the standard way you do it, and it will break down if your function is actually not conservative. Right? So, the summary of the method is the following, right? You're going to start with one of the partials, right? Like partial with respect to x. You're going to integrate to get to f. Then you're going to differentiate to get to the partial with respect to y. Then you're going to integrate again to get to f. And then you're going to be done, right? Once you get to this step, that's going to be the function you're after, right? So you're going to integrate, differentiate, integrate again, and we're going to match up the constants and stuff, and then we'll end up with our answer in the last part, right? So let's actually do the example. So here's my function, right? Now I know that this guy is fx, right? I know that this guy here is fy, right? Because I know the partials exist. So start with fx. Okay. So now we're at fx, what are we going to do? Go to f. How do you go to f from fx? Integrate with respect to x. Integrate this with respect to x. And what would I get?
X squared plus y squared x. Plus
Right, x squared plus xy squared, right? Plus some constant, right? Now your constant
actually it's g of y.
is going to be a function of y, right? Because if it was a function of y and you took derivatives, that part would go to 0 and you wouldn't see him here anyway. So you're going to assume that your constant is a function of y. So now we're at this step, we're at f. Where do we go next? To fy, right? If I have f, how do I get to fy? Well, I take a partial with respect to y of the function f. So I'm going to go with this and take the partial with respect to y. X is a constant, so that goes to 0. This guy would give me 2xy plus partial of g of y is just g prime. Right? Now this is equal to, by assumption, right? I said this was my fy. So if that's my fy and this is my fy, they have to be equal, right? This means that 2xy is equal to 2xy plus g prime of y. So in other words, my g prime of y is equal to 0, which means my g is just a constant, right? Because if you take the derivative of a constant, you get 0. But what do we know? We know that f is actually equal to x squared plus xy squared plus g, right? But my g I know is a constant. This means that f is x squared plus xy squared plus some constant. And that's going to be my function. And you can always do a check, right? If you find the gradient of this f, it's the partial with respect to x in the first component, that's 2xy plus y squared, right? Derivative of that is 0. Partial with respect to y, this would be 0, this would be 2xy, right? Which was the function that we started with, right?
So we can't figure out the constant unless we have some sort of initial value.
Right, you can't figure out the constant without initial values. But remember, the whole point of us doing this is to plug into the fundamental theorem for line integrals, in which case the constants would cancel anyway.
Yeah.
So in applying our theorem, the constant won't even matter.
That's the scalar function?
No,
This is the scalar function, yes. This is the scalar function that when I take its gradient, I get f. Right?
You get the vector field.
Yeah.
So why do we need P to be equal to do this?
Because these wouldn't match up. Right? If when I'm integrating and I set this equal to that, it's not going to match up. Unless the equation I had before was true.
But isn't P, if you take the partial derivatives of P and Q, isn't that just like the second partial derivative of the first function? Of the original? And that doesn't always match up?
I didn't. I integrated P and then I differentiated to get Q. So I never hit the second partials at any point.
No, when we needed the partial derivatives to equal to each other, isn't that just taking the second partial derivative of the original function? Why does that have to be equal?
Oh, you mean the partials of this guy?
Yeah.
Oh, well, like I said, if you write it out, you'll see why it had to work. If that wasn't true, this connection wouldn't work. I mean, it's just a manipulation thing. If you work out the algebra, you'll see that I need this to happen.
and why should cancel out?
Yeah. Let's do another example. Oh, I actually didn't do the second method. Forgot about that one. Alright, so method 2 is, here we're just going to do integrals. We're not going to do this back and forth and setting this equal to that and stuff like that. We're just going to integrate everyone, right? So you integrate p with respect to x, integrate q with respect to y. Those are pretty much it. Just integrate everyone and match up the terms.
If you feel comfortable doing method 1, do you have to bother learning method 2?
No?
No. For the exact formula, since we actually have to check it on while using the formula, there's no need to check it twice.
Mm-hmm.
For the exact formula, since we check it when using the formula, we don't need to check it twice, right?
No. I mean, I would to be safe, but you don't.
Okay.
Or if you're sure your first check is correct, technically, if you did everything correctly, you don't have to check it. So let's do the same example again. This was, what, 2x plus y squared, 2xy. Alright, so here's the thing. We know that f is equal to the integral of fx dx. So this would give me, just integrate this with respect to x. Which is x squared xy squared plus some constant of y. Also, f is equal to the integral of fy dy, which is just the integral of 2xy dy, which is just xy squared, plus some other constant of x. Right? Alright, so you just integrate each part with respect to the variable you know that you should integrate with respect to. Right? So that's the first step. The terms of your scalar function are just the terms that show up here, but no repeats, right? So if you had, notice that this function shows up in both terms, you don't repeat it, you just write it down one time. And you also ignore the constants of integration, so just forget those. So your f is just going to be equal to, an x squared shows up, so write down an x squared. Xy squared shows up, so write down an xy squared. And those are the only terms that show up, plus c. That's your function. Okay?
You said to ignore the constant, right?
Yeah, just ignore those and just put a plus square.
And the function constant.
Yeah, but on both sides, there should be some sort of repeating somewhere, right? Like there should.
You don't have to have repeats. You don't have to. But if they are, if you have this guy shows up both times, it doesn't matter. Just write it down one time.
No, but if you have a repeat, then you know you got it pretty much correct.
Yep. And again, you can always do the check at the end. If you want to be super safe, then you'll get it. Okay? So there are the two methods. The one you learned in 391, and then there's this one you can do, just integrate each component and just match up the terms. Right? Just pick out what you need to get your scalar function. Let me start the second example over here. So it's a three-dimensional function. I didn't show you how to check that yet, but I just said assume it's conservative, find the potential function, right? So in 3 dimensions, the same processes apply, it's just a little longer. You have to have a little more stamina, that's it.
Professor,
Yeah?
so for method 2, just make sure the catch is no repeats and just a no constant.
Yeah, but the bigger catch is that this will always work, right? Once you can actually integrate your terms, right? Even the second one that we know wasn't conservative, if I actually did this process, I would end up with an answer, right? There's really nothing to stop me. The first method, though, you have to realize that I came to a point where I had to go back and set something equal to another term, right? So there's this sort of interplay going on that it guarantees that things will work out at the end. This one, I really didn't interact the two, right? So it would have worked no matter what I put there. So that's something you have to really be careful with. So especially with this method here, doing a final check is advised, right? With the first one, if you do your derivatives and integrals correctly, you should not have to worry about it.
What does it mean by like no repeats?
They don't repeat.
No repeats, like here. You look at this guy, he's repeated here, right? So he shows up twice, but I don't write him down twice. I only write him down once.
Okay.
That's what no repeats. Don't repeat a term just because it shows up more than once. Is what I want to say. Okay. So now we're going to do for a three-dimensional guy. Let's talk about method 1. So in method 1, we're going to do a very similar thing. Fx, go to f, then go to fy, then go back to f, then go to fz, then go back to f. You basically have to cycle through all the partial derivatives there are and keep jumping back and forth between that and the function. So that's going to be the method. So now we can just...
So very long then.
yeah, it gets longer. The method 2 is usually shorter. It's just that for some reason it's not usually taught. Like the method isn't done in your book, method 2. I don't know why, but it's usually not taught, and it will pretty much work all the time. So you'd have to be careful when you're using it. So let's begin. I know that fx is equal to e to the x cosine y, right? This means that f would be equal to the integral of that guy with respect to x, which is going to be just itself, plus a constant now of y and z, right? Because the functions of y or z only show up, they would all go to 0, you wouldn't notice them, right? This means, all right, so now I start with f of x, I went to f, now I'm going to f of y, which means I'm going to differentiate this with respect to y. So this means I would get minus e to the x sine y plus the partial of this guy with respect to y, right? Because I'm differentiating with respect to y. Now this is equal to, by assumption, fy should be equal to this term over here. So I'm going to set it equal to that term. Nothing, right? So this, guys, this means that your gy is just equal to 0, which means that your g is just a function of z, right? Because if you differentiate that, you get 0. So I was at fx, f, now I'm at fy, now I'm going back to f. My f is here, and I now know what this function is. So this means f is actually e to the x cosine y plus some function of z. Now I'm going to go to f sub z. That will go away. This would just give me the derivative of that guy. This is equal to, by assumption, to 2. This means that k prime of z is equal to 2, which means that k of z is just equal to 2z plus a constant. Therefore, my f is actually equal to e to the x cosine y plus the k, which is just 2z. And that's my function, right? And of course, you can do the check. If you actually find the gradient of this guy, you will get that back. Any questions on method 1? Does anyone who has never done 391 actually prefer method 1? So, at least for teaching purposes, I prefer to use method 2 all the time anyway. So, after this, I'm pretty much going to always use method 2 when I'm doing this stuff on the board. It's just less writing for me and stuff. So yeah, let's do method 2. What does method 2 say? Well, you just integrate each part, right? We know that f is equal to the integral of e to the x cosine y dx. So I do that, which is just e to the x cosine y plus some constant of y and z. Also, f is equal to the integral of minus e to the x sine y dy. That's just e to the x cosine y plus some other constant of x and z. Also, f is equal to the integral of 2 dz, which is just 2z plus some other constant of x and y. This implies my f is equal to, just write down each guy that shows up. This guy shows up, he's repeated here, ignore it. This guy shows up, so it's just e to the x cosine y plus 2z. Okay? Yes?
Is it always going to be plus C, or is C going to be a set count?
Yeah, c is just an arbitrary constant.
Is it always going to be just the arbitrary, or is it?
Yeah, it's always arbitrary. I mean, you can't find it unless you're given some initial condition or some value of the function at some point. But for our purposes, you would never actually have to know the c, so I wouldn't worry about it. Right? That's a good enough answer. Any questions on the method? Alright, so now we're actually going to do a problem where we actually use it. It's a typical example, right? You'll see problems like this on your final and stuff like that. So here it is. For the vector field f equals Or this one?
Well, how do you do that? I mean, we don't know if it's conservative or not.
Yeah, well, if I tell you to find its potential function, it would be obvious that it's conservative. Because you can check that all these functions here, they're polynomials and trig functions. They're continuous everywhere, differentiable everywhere. So that condition is automatically fulfilled. It means that if you can find such a function, then it's automatically conservative. So it goes without saying here. All that is implied in the question itself.
So you don't have to check.
No.
Wait, so that's
There will be, you could have a problem where you have to check, but I didn't show you how to check for three-dimensional vector fields yet, so I can't ask you to do that now. But you could also be asked a question like this. It will be implied that it's conservative.
Okay. So we can. So
Because you would know the theorem
Like
that I
saying
gave
it's
you
true.
earlier that says, oh, it's continuous and differentiable, then
Okay. So
once I can find a function, it means it's conservative.
Okay, so that's true for any polynomial and.
Yeah, for any nice function, right? This is continuous everywhere, differentiable in the entire 3 space, you know.
So what's this?
None of that is a problem. Okay, so yeah, we give you a vector field. I say find its potential function, right? So let's do that. I'm gonna just jump into method 2. I know that f would be the integral of the first component. With respect to x. Right? What is that? What's the integral of this with respect to x? Yeah?
E to the x.
That's either x.
E to the xy.
Yeah.
Right?
Yeah.
What's the integral of this
Oh,
with
right, yeah. So that's
What's the integral of this with respect to
sine
x?
x is minus the sine of
X, that's sine xz.
Nine-
I mean,
minus
cosine.
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 Plus cosine.
No. No.
Plus cosine, right?
Plus cosine
Plus
xz.
cosine.
Plus cosine xz.
Plus
Right?
cosine xz.
And that's it, right? So it's plus some constant of x and y. X and z. Y and z. Right? Which we're going to ignore that anyway. Also, right, so you have to remember your integral and differentiation. F is going to be equal to this guy with respect to y. Right? Now integrate that with respect to y, I get e to the xy
Plus y cubed over 3.
plus y cubed over 3 plus some other constant
Yeah.
of x and z.
Do we have to write like that, or can we just write c?
Oh yeah?
Do we have to write it with?
Yes, you have to write
parameters?
like that.
Okay.
Because it doesn't have to be a constant, or it could be. If I had a function of x and z here, then when I differentiated,
Yeah, but
they
it
would
won't.
disappear.
But it won't matter if for purposes though.
For the method, it won't matter. You should know that it should be there. And this part, I'm going to integrate the last component with respect to z. Integrate that with respect to z, what do you get? Just cosine xz plus some constant of x and y. Therefore, your f is equal to, write down all the guys that show up, and e to the xy shows up, plus cosine xz shows up, plus a y cubed over 3 shows up.
Do you have to write over 3? Because that's when you said ignore constants.
Ignore the arbitrary constants of integration. These are the guys you ignore.
For there was an example where it was y2 over 2, but you didn't write over 2 in the answer.
Where was that?
Probably because it was divided. Two was already being divided.
Oh,
Yeah, this is not a constant. This is a function. and plus, now you put in the arbitrary constant. All right. Now, since I did the shortcut method, I'm going to check my work. All right, so you can write it out or just check it mentally, but you have to do a check. So, check. If I find the gradient of this guy, right? Differentiate this with respect to x. This is 0, that is 0. Differentiate that with respect to x, I just get y e to the xy. Derivative of cosine is minus sine this times the derivative of that, which is z. Sine is z. And that's the first component.
You only need one, right?
Now, if I differentiate that with respect to y, I would get x e to the xy. This part is 0. This part would just give me y squared. And the constant is 0. Now, if I differentiate with respect to z, these are all 0, and I just do this guy. So that would give me minus x sine z. And was that the guy? Yeah. Yeah. So it works. Okay. Part B.
If
Yes.
you, alright, so after we learned how to check it in 3 dimensions, if instead of checking it, we tried this, and then we checked it with this part, and it didn't work out to the same thing, then we know it's not a potential. Then we know it's not conservative.
Right.
then
So
it's
if
still
you
a
did this
check.
and your final check doesn't work out, there are two options. Either you made a mistake while integrating, or it actually doesn't have a potential. But of course, if I ask you to find it, it's going to be there. I'm not going to give you that kind of trick.
Wouldn't we have to check to see if it's all equal? Like exact?
No, it's 3-dimensional.
This is a 3-dimensional. The check is different. It's not the same thing, right? That check I can only teach you after we cover like 2 sections away. So we'll cover that later on. Here it's just sort of implied. Anyway, so here we're going to do part B. Okay, now remember how to do f dot dr. What do you do?
It's the dot product of the.
You find r,
Yeah,
you find dr,
the
you
r.
find f of rt, you dot product them, you integrate, right?
Yeah, of R. The,
Okay.
the derivative
So-
of R and f of R in it.
Right. So now we're not going to do that. Exactly. This is the trick question. It's exactly the kind of question I put in an exam to trick you. Just take a second to appreciate that if you actually did that, right, differentiated this, plug in x equals t, y equals t squared plus 1, and z equals 2 sine inverse into this function. Dot product those, imagine the kind of monster you'd end up with, right? You take the whole exam doing that integral. The trick is to not do the integral. Since a potential function exists, the fundamental theorem for line integrals applies. It means then that my f dot dr is just going to be equal to this potential function, this same one that I just found here, evaluated at the last endpoint, minus that function evaluated at the first endpoint. There's no way I'm going to do that integral directly. That's crazy. And
Wait, so we need to actually write that down? We can't say that since.
no, well, I mean, if you just write this down, this line here, and then actually do it, that's fine. I'm writing this down for instructional purposes. I'm explaining why I can do this. Because I know it's a potential function exists, that implies it's conservative, which implies fundamental theorem for line integrals exists. All the components are continuous, everything is nice, right? Now, I know that this is the point, this is like the A, right? This is like the B. Right? This implies that integral along C of f dot dr is going to be equal to f evaluated at 0, 1, 0, at, sorry, 1, 2 pi minus f evaluated at 0, 1, 0. So you go to this function here, and I'm going to plug in x equals 1 and y equals 2. X equals 1, y equals pi. Cosine of pi is what?
Minus 1.
Negative
Negative 1.
Negative 1. Okay, and I'm going to plug in y equals 2 over there, so that gives me 8 over 3. Minus, of course I don't have to put the plus c because you're just going to die over here. Minus, now I'm going to plug in x equals 0, so that just gives me 1. Cosine of 0 is what?
1.
Plus 1.
You trying to
And
trick
then I
us?
plug in y equals 1. That equals a third. Right? So this is actually equal to e squared minus, this is 2 plus a third, right? Which is going to be what?
7/3.
What did you say?
2 plus a third is 7/3.
7/3.
7, I thought you said 10/3.
What?
Okay.
Ah.
Right. I'm just making sure. Right? So it's going to be minus 7/3, which gives you what?
So
8/3 minus 7/3 is 1/3, right? And 1/3 minus 1 gives you minus 2/3. Now, wasn't that a lot nicer than after actually doing that integral? If you had done that integral, if it was even possible for you to have integrated that, this is the answer you would have ended up with. Right? But because I know a potential function exists, it means it's conservative, which means I can just use the fundamental theorem for line integrals, and that would actually be the answer for f dot dr. Right? So for a problem like this, you would not be expected to do the integral directly, but of course, you have to know that. That's it for today.
Wait, so is the section done now?
This section is done, which means the homework is due
On next class.
next class, which is next Wednesday, I
Yeah.
believe. The first test, I think I'll make it the Monday after that. Yes, next week you have a quiz. It's going to be on everything we covered since the second quiz. Yes. So,
Because that's 13.2.
so it'd be on the 25th, right? Yeah, so test 1 is on the 25th. So write that down.
Either, yeah.